Lab 6 deals with the measurement of passive elements using a network analyzer. Spectrum analyzers allow a visualization of only the magnitude of an RF signal. With a network analyzer, we'll be able to look at both the magnitude and the phase. This will allow us to measure RF components at very high frequencies. As you've seen in the course, resistors, capacitors, and inductors have limitations at high frequencies. Models of these components are actually made up of idealized resistances, capacitances, and inductances. But all of these are going to resonate at a given frequency. We're going to use a network analyzer to determine what's the upper usable frequency of our component before these other non-ideal effects kick in. The concepts covered in this lab are phase plane adjustments, equivalent circuit of a resistor, equivalent circuit of a capacitor, equivalent circuit of an inductor, and a formula for winding an inductor. The laboratory techniques we're going to cover are calibrating the network analyzer, de-embedding the test fixture, measuring the reflection coefficient, and extracting impedances versus frequency. In lab, we have an HP 4396B network analyzer. The network analyzer measures signal amplitude and phase versus frequency. Using a network analyzer, we'll be able to measure electronic components over a wide frequency range. What's shown in the next page in Figure 1 is a block diagram of our network analyzer. The 4396B network analyzer contains 3 superheterodyne receivers to detect the reference, reflection, and transmission inputs. The detectors at the end of the superheterodyne receivers demodulate the inputs into real and imaginary components X plus JY. That would be over here, which contain the magnitude and phase information. The RF output is a sweep generator which sweeps all frequencies in the range that we're going to be measuring. To make measurements, external equipment has to be added to the 4396B. We're going to use the 85046A S-parameter test set. The setup is shown here in Figure 1. An external directional coupler allows the network analyzer to measure S11 and S21 for a device under test. To measure S22 and S12, we have to reverse the connections on the device under test, and our 85046A can do that automatically. Now, every time the network analyzer is turned on, or the frequency settings are changed, a calibration must be done. We're going to use shorted, opened, and matched load terminations to calibrate the network analyzer. Once this is done, we can take our measurements. We'll be taking our measurements at a phase plane or at the connector terminations. Usually we change the phase plane. This is shown in Figure 2. So here will be our RF board in lab. We'll have connectors on these two sides. And this is really a microstrip. And we'll be taking measurements out here on a device, but our connections will be back over here. Now to change the phase plane, the time delay can be programmed into the network analyzer. There's a lot of ways to do this, but there's a thing called the port extensions option. And the port extension option allows us to effectively move the measurement from the connector here to this position. It's pretty much like using a slotted line. Effectively what we're doing is just programming a delay, as shown in the ebook lecture notes. In this lab, we're going to measure an impedance Z, which is connected to the microstrip line shown in Figure 2, which is a transmission line consisting of a strip conductor and a ground plane separated by a dielectric. With the network analyzer, we're going to measure S11, which is actually gamma 0. The relationship between gamma 0 and our impedance that we're measuring and the characteristic impedance is shown here in equation number 1. We can solve from equation 1 the value for Z in terms of Z0 and gamma 0, as shown in the lecture notes, where Z0 is a characteristic impedance and Z is the impedance that we're measuring. And we're going to be measuring our R, L's, and C's in our lab. The first one's going to be a resistor, and in the ebook lecture notes, in Chapter 1, there's a model for a resistor, which consists of an ideal resistance, inductance for the lead on the left side, and inductance for lead on the right side. Now there is some resistance that's kind of lumped into the value of R. Usually R is much bigger than a few hundred milliohms, so basically just dominated by the resistance value. And then between the outer connections of the resistor, there's effectively some capacitance. Here's a normalized plot of the impedance of various resistor values versus frequency. These are carbon metal film resistors. So for low values of resistance, it pretty much looks like an RC circuit. In other words, the L doesn't have much of an effect. If you're using a carbon composition resistor, these are much older types of resistors, they actually roll off at a lower frequency. These are typically used in vacuum tube guitar amps because they have a limited bandwidth just built in. And that will lower the noise in the system, as we'll talk about later in the course. Now, as the values of the resistors get smaller, the effective impedance of this inductor can now become noticeable or significant. You can see here for low values of resistance, we're getting a resonant peak, that the impedance of these two leads is large enough compared to R that we basically have a parallel LC circuit. So we're going to be measuring some of these frequencies in lab. As shown in the ebook lecture notes, we can also calculate the inductance of a piece of wire. We're going to use this to calculate the inductance of our lead length. And the value in nanohenries is equal to twice the length in centimeters times the quantity 2.3 times the log base 10 of 4 times the length in centimeters divided by the diameter in centimeters. We're going to use a conversion from wire gauge to centimeters. And that's 2.54 times 10 to the minus 3 times 2 raised to the 50 minus the gauge of the wire divided by 6. And then minus 0.75. Shown in figure 5 is a high frequency model for a capacitor, also shown in the chapter 1 ebook notes. And it consists of a capacitor in parallel with a very, very high resistance, thousands of megohms, and then in series with that in L and R, the effective series resistance, and then some effective inductance. We're going to lump both the leads into one value of L and one value of R. Now, as frequency increases, the impedance of the capacitor begins to decrease and swamps out the value of RFP, and what you've got is a series resonant circuit. And when it resonates, the L and C cancel, and basically we just have a resistance left over. So our usable frequency is below that resonant point. Now, in the chapter 1 ebook lecture notes, we talked about the Q of a capacitor, and that's equal to the reactance of the whole unit divided by the effective series resistance. An ideal capacitor would have an effective series resistance of 0, and that would make the Q equal to infinity. What's shown here in figure 6 is the impedance of the capacitor versus frequency. For frequencies below resonance, which is 1 over 2 pi squared of LC, because you have a series resonant circuit, the capacitor looks capacitive. Then as you begin to approach this point, it becomes purely resistive, and then past resonance becomes mostly inductive. So our usable frequency range is back here, where the capacitor looks like a capacitor. Now, inductors also have an equivalent circuit, as shown in the chapter 1 ebook lecture notes, where we have the inductance, and then effectively the resistance of the wires, and also the lead length, and then a capacitance between each of the turns of wires. As frequency increases, the impedance of the inductor becomes bigger than the resistor, and we effectively have a parallel resonant circuit. As with capacitors, inductors also have a Q, and it's equal to the imaginary part divided by the real part. Ideally, this would be infinite if the effective series resistance was 0. And on the following page, we'll have a sketch of the impedance of the inductor versus frequency. And so frequencies below resonance, the inductor is dominated by the inductance, and then as you approach resonance, the L and C cancel, and all you see is effectively a parallel resistance, as we discussed in the ebook lecture notes. And then above resonance becomes capacitive. Our usable frequency range is, of course, below this. We're going to measure these self-resonant frequencies with a network analyzer in lab. As you saw in the AM/FM radio, we had one of our own inductors that we stuck in. We're going to actually make one this week in lab, where the inductance is a formula that's again in the ebook lecture notes, where the inductance is in microhenries. It's equal to 0.394 times the radius in centimeters squared times the number of turns squared divided by 9 times the radius plus 10 times the length, which is in centimeters, provided that the length is greater than 2/3 of the radius. Now, before coming to lab, I'd like you to make a 300 nanohenry inductor by picking the number of turns if the radius is 1/8 of an inch and the length is 1/4 of an inch. Now, make 2 copies of your calculation, submit one derivation to your lab instructor at the beginning of lab, and keep the other for your work in the lab. This will be a pre-report and will count as part of your lab grade. And this is the background for lab number 6.